Betelgeuse is a huge star, perhaps 15 or multiple times the mass of our Sun, and it's close to the furthest limit of its life. It is an enormous, tremendous, glowing star, and one day it's going to go blast. When you consider stars detonating, what rings a bell is some kind of tragic fiction. You'd never envision it could happen. In actuality, Brian Cox has terrible news available for everybody. The Betelgeuse star is detonating. And in addition to the fact that it's true, it's also very close to Earth. Now, the question at the forefront of everybody's thoughts is, what does it mean for a star so close to Earth to detonate, and how does that completely change our lives here? Join us as we explore Brian Cox's warning about the approaching Betelgeuse cosmic explosion, the approaching blast. When Brian Cox, BBC's resident science communicator and widely acclaimed physicist, raises something science-related on air, people tune in. And when that something happens to be an immense star multiple times bigger than our Sun, in danger of detonating soon, you can understand why lots of people are frightened. But what is the present discussion about detonating stars? Betelgeuse, also called Alpha Orionis, is perhaps one of the most recognizable stars in our night sky, yet its importance extends beyond simple visibility. Named a red supergiant, this gigantic star is located in the constellation Orion, marking the hunter's left shoulder as we see it from Earth. In terms of size, Betelgeuse is a true giant, with a radius around 700 to 1,000 times that of our Sun. It also weighs anything from 15 to 20 times what our 5-billion-year-old Sun does. The star's life is driven by internal tensions, with atomic fusion pushing outward against the gravitational forces pulling inward. This equilibrium has kept Betelgeuse stable for a long period of time. However, as the fuel for fusion diminishes, Betelgeuse has become unstable, leading to dramatic changes in brightness, temperature, and size. It is believed to be in the final stage before it eventually implodes and detonates as a supernova. The extraordinary darkening that occurred in 2019 has been taken by the broader scientific community to be a distinct marker of this instability and the approaching blast. The extraordinary darkening of Betelgeuse, as it has come to be called, is something that began in late 2019, catching the attention of both professional astronomers and casual stargazers alike. Essentially, scientists were able to see that the light emitted by the Betelgeuse star, which is regularly the 10th most luminous star in our skies, somehow had its light dimmed suddenly by almost 40%. This phenomenon was first observed by amateur astronomers, who were familiar with Betelgeuse's usual brilliance, and they then alerted the rest of the scientific community. The red supergiant, long known for its normal and predictable fluctuations, had never shown such an extreme drop in luminosity. As this phenomenon advanced, it became the focal point of intense hypothesis and debate among researchers. The questions being asked were straightforward ones. What was causing this extraordinary dimming? Could it be a sign that Betelgeuse was about to go supernova? As is common in science, however, the answers were more complicated than that. Several theories arose to explain the sudden change in brightness. One leading explanation, proposed by a group from the Harvard-Smithsonian Center for Astrophysics, suggested that Betelgeuse had ejected a massive dust storm, which might have blocked some of the light from reaching Earth. Their observations, based on data collected from their telescope and research, showed that part of the star's southern hemisphere had cooled significantly, possibly leading to the formation of dust particles. This explanation aligned with the behavior of other red supergiants, which often lose material as they approach the end of their lives. This process, like other red supergiants, involves what is known as a vigorous convective cell, generating shock waves and ejecting gas from the star's surface into its outer atmosphere. The gas, passing through the atmosphere, cools, condenses, and forms dust and other materials. Another hypothesis, put forth by a group of researchers from the Max Planck Institute for Astronomy, suggested that the dimming might have been caused by large convective cells on the star's surface. These cells, which are responsible for moving heat from the interior of the star to its outer layers, may have temporarily cooled, causing Betelgeuse to appear dimmer from our perspective. Despite these well-supported theories, some others speculated that the dimming might be a precursor to a supernova. This led to some widespread panic that ultimately prompted figures in science like Brian Cox to address the possibility and implications of a supernova occurring. Yet that's not nearly all there is. While Betelgeuse isn't expected to detonate for another 100,000 years, the strange behavior led to questions about whether the star may be closer to its end than previously suspected. This theory, though more uncertain, sparked interest among established scientists, as a supernova occurring in such proximity to Earth would provide a rare opportunity to study. As the dimming continued, instruments like the Hubble Space Telescope were directed toward Betelgeuse, gathering critical data to help unravel the mystery. These observations not only provided insights into the cause of the Great Dimming but also offered valuable information about the processes happening in Betelgeuse's outer layers. Before we explore the role that the Hubble Space Telescope played in observing the Great Dimming, let's establish some facts about this very massive star. What do we know about the Betelgeuse star? We know that the Betelgeuse star is about 700 light-years from Earth, although this estimate can vary due to the challenges in measuring such vast distances. This means that any sight you catch of the star is essentially from 7 centuries ago, since light-years refer to the time it takes light to travel that distance. And no, before you ask, there's nothing scientifically proven to travel faster than light. Studies have shown that a blast strong enough could potentially cause a mass extinction event, even a few light-years from where it originated. As for its mass, Betelgeuse is about 15 to 20 times greater than the Sun's. However, it has expanded so much in its current life stage that its density is incredibly low. Interestingly, the star is only about 10 million years old, much younger than our Sun. But because it is a red supergiant, it will burn out much quicker than our own. This is why we are in a position to observe what could possibly be its last moments. The color of Betelgeuse, a dark red, is an indication of its cooler temperature, around 3,500 degrees Celsius, which is significantly cooler than our Sun, which burns at about 5,500 degrees Celsius. This color not only indicates its temperature but also its stage in life. This is important because Betelgeuse is nearing the end of its life cycle, having burned through the hydrogen in its core. Now, it is fusing heavier elements like helium, carbon, and oxygen, which is typical for a star in its final stages. Scientists knowing it's in its late stages is how we know we could be near seeing a supernova more than ever. Throughout history, Betelgeuse has been a subject of interest across many ancient civilizations. The Romans noted its brilliance, ranking it among the most prominent stars in the sky. Chinese astronomers referred to it as Shen, a reference to their dragon star system. Arabic astronomers who named it Bu derived the term from Yad Allah, meaning the hand of Orion. These ancient civilizations did more than admire Betelgeuse's brilliance. They observed its changes over time, recording its fluctuations in brightness. The dimming and brightening of Betelgeuse have been recognized since the first recorded observation of its variability by astronomer John Herschel in the 19th century. As you can see, this giant star has been on a clock for a long time, but the current phase of its development suggests that Betelgeuse could be nearing the brink of what scientists are calling a dramatically powerful finale. Now, let's shift our focus to the events surrounding the Great Dimming and the crucial discoveries the Hubble Space Telescope revealed about it. There, you'll begin to see the most undeniable evidence of Betelgeuse's looming fate, and why it could change our lives like nothing else before it. Hubble Space Telescope's observations of the Great Dimming. The Hubble Space Telescope, one of the most valuable tools for astronomical observation, was crucial in understanding the Great Dimming of Betelgeuse. In mid-2020, astronomers used Hubble's ultraviolet capabilities to monitor the star's outer layers. Their findings revealed that Betelgeuse had indeed expelled a massive amount of hot material from its surface. This material, traveling through space, cooled and condensed into a dust storm, which, if not the originator, likely contributed to the dimming. This ejection of material, identified by Hubble, was one of the largest events of its kind ever observed in a star of Betelgeuse's size. The expelled mass was equivalent to several times the weight of the Moon, an astonishing amount of material to be lost by a single star. It was so massive, in fact, that the cloud it created covered over 100 million miles of space, stunning observers. When Betelgeuse began showing signs of increased activity as the Great Dimming peaked in mid-February 2020, astronomers were closely monitoring the star using every available instrument. The ultraviolet observations made by Hubble gave scientists an unparalleled view of Betelgeuse's dramatic behavior. These observations began just as the dimming started, allowing astronomers to trace the sequence of events that led to the star's sudden change in brightness. By studying, during the incomparable diminishing, significant bits of knowledge into how red supergiants like Betelgeuse lose material in their last phases of life were revealed. Understanding this cycle is crucial for predicting when and how these stars will ultimately detonate as a cosmic explosion. The observations also raised new questions about how frequently such mass discharges happen, and whether they are a standard part of Betelgeuse's life cycle. The implications of these findings are sweeping, especially for theories about cosmic explosion formation. The fact that Betelgeuse is losing material at such a fast rate suggests that it may be approaching the end of its life sooner than previously suspected. However, despite this tempting possibility, astronomers remain cautious, noting that while the star's behavior is unusual, it is not enough to definitively confirm that a cosmic explosion is imminent. Hydrodynamic simulations have been especially useful in modeling what could occur next with the star, and the results of these advanced recreations, combined with the star's later behavior, present an image that is quite ominous. Betelgeuse's new behavior in hydrodynamic simulations, soon after the Great Dimming, has continued to be erratic, leaving astronomers both fascinated and puzzled. One of the most significant developments in understanding its new movement has come from hydrodynamic simulations. These advanced models mimic the interior processes of stars like Betelgeuse, giving researchers a glimpse into the hidden forces that are driving its instability. One key finding from these simulations is the role of convection in shaping Betelgeuse's erratic behavior. Convection, the process by which heat is transferred from the center to the surface, has become increasingly turbulent as the star approaches the end of its life. Large convective cells on Betelgeuse's surface rise and fall, causing the variations in brightness that we can see from Earth. These simulations suggest that the star's outer layers are becoming progressively more turbulent. Another factor contributing to Betelgeuse's instability is its cooling temperature. As the star cools, its outer layers expand and contract, leading to changes in brightness and shape. This cooling is part of the normal process for a red supergiant, but in Betelgeuse's case, it has become more pronounced recently. The simulations show that this cooling could be a precursor to more dramatic changes in the star's structure, again possibly signaling the beginning of a cosmic explosion. These studies have led to Betelgeuse's new behavior being compared to that of other cosmic explosions. One notable example is SN 2023 YAF, a cosmic explosion observed in the constellation More Chaotic 101 sometime in May of 2023 by Kiichi Itagaki, an amateur astronomer responsible for discovering over 100 cosmic explosions. In 2023 YAF, like Betelgeuse, involved a red supergiant in its last phases of life. The collapse of the star's core led to a massive explosion, releasing a tremendous amount of energy and creating a bright spectacle visible from Earth. The similarities have led researchers to draw parallels between SN 2023 YAF and Betelgeuse, noting that similar processes could be taking place in both stars, although the former was observed later, as it was seen in the extreme stages of its destruction. It could provide valuable lessons for studying the Betelgeuse star, which has yet to fully regress. The discovery of SN 2023 YAF was significant not only for what it revealed about cosmic explosions, but also for the insights it provided into the progenitors of these blasts. Observations of the explosion showed that a dense shell of gas surrounded the star at the time of its collapse. This shell likely formed from material expelled by the star in the years leading up to the explosion, playing a key role in shaping the final stages of the star's life. The presence of this shell has led researchers to speculate that Betelgeuse, with its history of mass launches, including the one occurring during the Great Dimming, may exhibit similar behavior. As researchers continue to monitor Betelgeuse, comparisons to SN 2023 YAF offer the entire community valuable clues about what could happen next. The hydrodynamic simulations, combined with real-world observations, have finally been enough to suggest that Betelgeuse is indeed nearing a critical threshold. While it may still be many years before the star detonates, the evidence certainly points to an eventual cosmic explosion. What remains is to understand when this explosion might occur and how it compares to other recorded cosmic explosions. But exactly how soon can we expect Betelgeuse to become a cosmic explosion, and what impact could it truly have on life here on Earth? The subject of when Betelgeuse will go supernova has captivated not only scientists but also the public. Many research groups around the world are dedicated to studying this very question, each offering their unique expertise and technologies of value. The general consensus is that Betelgeuse will indeed explode as a cosmic explosion, but when exactly that will happen remains uncertain. One of the leading organizations in this area of study is the University of California, Berkeley, where scientists have been using data from the Hubble Space Telescope and other observatories to model Betelgeuse's life cycle. Their findings suggest that the star is in the final stages of its red supergiant phase, meaning a cosmic explosion could occur within the next 100,000 years. While this may seem like a long time from our perspective, it is a mere blink of an eye in cosmic terms. Another prominent research team, led by astrophysicist Emily Levesque from the University of Washington, has focused on Betelgeuse's mass loss rate. Her group's studies have shown that Betelgeuse is shedding material at an accelerated rate, indicating that the star is rapidly depleting its fuel. This loss of material could be a precursor to a cosmic explosion as the star's outer layers become increasingly compromised. Levesque's group has used both ground-based and space-based telescopes to monitor Betelgeuse over several years, gathering data on its temperature, luminosity, and mass ejections. According to their calculations, the star's outer layers are behaving erratically, suggesting that it may be approaching a critical tipping point. However, even with these observations, predicting the exact timing of a cosmic explosion remains incredibly difficult. Cosmic explosions, by their nature, are unpredictable and erratic, often giving little warning before the blast occurs. Betelgeuse's potential cosmic explosion has also sparked renewed interest in historical cosmic explosion events with which to compare. The earliest recorded cosmic explosion comes from Chinese astronomers in 185 AD, who observed what is now known as SN 185. This explosion, located in the Milky Way, was visible for several months and was thoroughly documented, with descriptions of its sudden brilliance and slow fading. The event, which occurred long before the advent of modern telescopes, was one of the first known instances of humans observing the death of a star. Other significant cosmic explosions include SN 1054, observed by astronomers from China, Japan, and the Middle East. This event was the brightest recorded supernova in human history, even surpassing Venus in the night sky. The light from the explosion was visible for several months, and it had a lasting impact on those who witnessed it. Modern astronomers have used records of SN 1054 to reconstruct the event, and studies suggest that it was caused by a type I supernova, where a white dwarf star exploded after accumulating too much material from a companion star. Similarly, SN 1054 led to the creation of the famous Crab Nebula, which remains visible to this day. The explosion, observed by Chinese and Japanese astronomers in the summer of 1054, left behind a pulsar, a rapidly rotating neutron star, in a cloud of gas and dust. More recently, Kepler's supernova SN 1604 was observed by Johannes Kepler in 1604. This event marked the last supernova observed in the Milky Way and was significant because it helped astronomers understand the process of stellar death and the aftermath of supernova explosions. The remnants of SN 1604 continue to be studied today as part of ongoing research into supernova remnants. One of the most important supernovae for modern science, however, is SN 1987A, which was observed in the nearby Large Magellanic Cloud galaxy. This supernova has been crucial in helping researchers develop models of supernova behavior, as it was the first event to be studied using modern instruments. Observations of SN 1987A have provided insights into the processes that occur during a supernova explosion, including the formation of neutron stars and the release of neutrinos, tiny particles that pass through matter with almost no interaction. These neutrinos were detected during SN 1987A, confirming theories about their role in supernova explosions. The study of these past supernovae has been instrumental in shaping scientists' understanding of what could happen when Betelgeuse finally explodes. Each event has contributed to the growing body of knowledge about how stars die and the effects their deaths have on the surrounding universe. As Betelgeuse's behavior becomes more unpredictable, scientists continue to compare it to these historical supernovae, searching for patterns that could help predict when the next big explosion will occur. Understanding the timeline of Betelgeuse's demise is crucial not only for astronomers but also for the broader scientific community. A supernova in such proximity to Earth would provide an unprecedented opportunity to study the actual processes involved in stellar explosions. As we look to the future, it becomes essential to consider what Betelgeuse's eventual explosion might look like from Earth.